So this will be the second part of our Week 8 assignment about linear regression, Chapter 2 in the AP Stats curriculum. So for this question, they're talking about, let's see, the correlation coefficient right there. Now, they are expecting you to know that the correlation coefficient is the R value. So make that connection. And if there is a question that they're going to ask you on the AP, it's probably going to be interpreting the correlation coefficient. Now, back up in the context, there's an explanatory variable, or independent, and then there's a response variable. You've got to know that the X, or independent variable, is our explanatory, and the response is our dependent variable, Y. We plug in X to get Y, so that's usually how it works. So make sure you understand that concept. Now, as far as correlation coefficient goes, this is a strong positive. This indicates a strong positive linear relationship. It has to be the strength. Your choices are strong, moderate, or weak. You have to give the direction, positive or negative. And you have to say linear relationship. If anything is missed, it's typically that the linear is left out. So make sure that you include that word. Now, if there is context like there is in this case, you have to make sure you include it. Okay, so right here is where we'll show that. So between the there it is. All right. One thing I want to add to this while we're here is we'll show you the different strengths. I spoke about strong, moderate, weak. Okay. So strong will be anything from 0.8 to 1.0, and then I threw absolute value. That is because negative 0.8 to negative 1.0 is also considered strong. So absolute value, whichever side of 0 it's on, same description or strength. 0.5 is considered moderate, and anything under 0.5 would be considered weak. Okay, if you happen to get exactly 0.8, it doesn't matter if you put that in strong or positive. I'm sorry, strong or moderate. Okay, so right on the, I know I left out the border, but be careful when it comes to that. All right, number 4. It is reported that the coefficient of determination, okay, that is, they're not going to tell you that that's R squared. You have to know that that's R squared. So that's 88.7%. And they'll want the correlation coefficient from that. So we'll have to take the square root. Usually, I'm going to just slide over here. There's an example. We usually get that from here. So you'll see a display, and they'll typically give you R squared, okay, in a display like this. So I don't know exactly what computer generator they're going to use. Minitab is similar to this, but there's others. Just look for R squared, and what we're going to do, that is the coefficient of determination. Very closely related to correlation coefficient, but you got to know the difference. So write that down, keep it next to you when it comes time for the AP. All right, so how do we calculate first the correlation coefficient? Tricky. R squared, she's going to be capital, but when we convert it's lowercase. If that's 88.7%, you don't want to take the square root of it as a number like this. First move, believe it or not, you have to convert it to just a decimal, and then you can square root. Oops. And this is going to be weird. Take the square root of both sides. You know from A2 that you should put plus or minus in front of it. And to get that, so I'll quick get this calculator. 0.9418. Oops. All right. Now, I know it's negative, and that is because of an above average value for x tends to be related to a below average value for y. So let's express what's happening here. There's two choices. You could have a positive linear relationship, or you could have a negative. Let's draw them both. All right. Now, in every one of these, the line of best fit will hit the point, every line of best fit hits the point where x bar, y bar meets. Okay. Now, to the right are your above average values of x. Okay, those are your below average values of x. We wanted above average values of x, so we're thinking, all right, go to the right. Now, what is that related to? Well, it's related to below average values for y. Well, these, if you look, these are above average values for y. So it's not a positive relationship. Let's check out in the bottom. Okay, so let's say that's x bar, so that would be y bar. If that's the average value of y, these are below average values of y. Those are above average values of x, and that's what we wanted. So that indicates a negative linear relationship. Now, we can't forget, now that we've got that it's negative, we have to interpret. Okay, so again, it happens to be in the strong range. So we'll write that this is a strong equals negative 0.948. Right? Indicates a strong negative linear relationship. Okay, now we have to look at context. They didn't give context, so now we can say between the variables x and y. That's it. Explaining, this diagram does in fact explain why we indicated negative. So, good enough. All right, residual. I want to talk about residuals. First, deriving. Okay, so if we have a line of best fit, some of our data points are going to be right on the line. Some are going to be above, some are going to be below. I'll throw another one up there. Now, a residual is any vertical distance between a point and the line of best fit. Residual is how far off that particular point is from our prediction. So that is a residual. Now, a little bit tricky. When the point is above the line, it should be a positive residual. When the point is below the line, it should be a residual that is negative. Okay, so make sure that you comprehend that. Now, this is a data point that is an actual piece of data. So 3271 means there was actually a data point when x was 32. There was an actual data point of y is 71, not the prediction, the actual. Okay, they gave us the slope and the y-intercept. All right, y hat is the line of best fit, the equation for the line of best fit. We can calculate y hat by plugging in our value of x. And in this case, we would get y hat to be 69.44. Now, that's not what actually happened. What actually happened was 71. So there was a small difference from the line. The data point was above the line, so we should get a positive residual. So the residual is actual minus predicted. (71 minus 69.44). So the residual was 1.56. Let's see, is there anything else that we have to say? No, just what is the residual? Good enough. That's the value of the residual. All right, for the next one, we want to write the equation for the line of best fit. Now, there's going to be some formulas that are on the formula reference sheet. So if they ask you for this, here are the formulas you should be looking for. To calculate the slope from summary statistics, it has to give you the R, the standard deviation of Y, and the standard deviation of X. And you can calculate the slope from that. The y-intercept, they actually didn't have to give you a formula for. They might not. But if they do give you one, it's the average Y value minus the slope times the average X value. Now, you know that one of the points on the line of best fit is always the average X, average Y, so that they don't even have to give you this formula. All right, so let's calculate the slope and show it. All you got to do is show, there's your correlation coefficient, R times. Careful on this, make sure you put SY on top. Okay, so B1, I get negative 1.134. All right, this is important to understand that the correlation coefficient has to have the same sign as the slope, and then there's Y. Standard deviations are always positive, so that's how you get a positive slope, or a negative slope. All right, so for B sub 0 is the y-intercept. Now this is just stats. Obviously, we call it something different in our, algebra. We call the slope M, and we just have this as B for the y-intercept. But they have different letterings for those. So make sure you get accustomed to that. All right, y bar is 31.5. Just plug in and then let the calculator do all the work. Careful with the double negative here. Don't want to mess that up. Let's see, B sub 0, I got 83.43. And just put it all together. So y hat, negative 1.134. There it is. I don't think we have to, just show the work. Okay, last concept is residual plot. This is a scatter plot where you have the x values and the residuals. Okay, so if we go back up here to this concept, you would be plotting for this x 0 basically for the residual, right? Because it's right on the line. Okay, so the residuals will get plotted relative to the x value. Now, what you're supposed to be looking for is, does that look just these points are random on the scatter plot, or is there a curved pattern? Now, I'll show you in the next question. It will be distinct. If there's a curved pattern, it will be really obvious. So if you're searching hard to find a pattern, it's not there. What we would say is this is random. Now, when the residual plot is random, okay, you'll say that. It looks like it's random, which tells us the linear model is appropriate. That's all you have to say. There really isn't any more than that. Now over here, what we have is the distributions of residuals. You probably won't need that because we're not doing inferencing. The distribution of residuals should be approximately normal, and that's if our process is reliable. But I doubt that we're going to need that because we're not covering Chapter 9 on this exam this year. All right, so let's jump right down to the residual plot on number 8. So when there is a distinct pattern, such as this, here's why. Basically what we're saying is, even if the correlation coefficient is high, you might have the wrong model. So I'm going to exaggerate it a little bit, but we could have an exponential function here, or power. There's a couple that are typical. Now our line of best fit would go like this. And I might have missed by a little bit, but let's say it does something like that. What you can see here is in the beginning, in these first few x values, notice that they are above the line of best fit. Then it's about the same, and then it goes below for a while. Then it's about the same, and then it goes back to the high. So this is above for low values of x. The residuals are negative or below for the middle, and then it's a pattern back to the residuals are above again. That shouldn't happen. It should be random. Across the x values, it should be all over the place instead of having this curved pattern. When it is curved pattern, what you have to say is the curved pattern in the residual plot now be careful here, tells us a non-linear model would be more appropriate. We're not going to take the risk saying that the linear model is not appropriate here. We're just going to say a non-linear model would be more appropriate. You should check out a non-linear model. And this tends to be confusing for students. When you get a high R value, they think that's the end of the story. Okay, my R value is 0.95. Oh, it must be the linear model is appropriate. Not always. You might get a situation where you have an exponential function and a linear model, based on the part of the data that we calculated, it might show that it's a very high R value. Again, that does not mean that the linear model is the most appropriate one. So be careful on that. I'm not sure that that'll come up, but in case it does, we're ready for it.